Hello all, welcome back to my YouTube channel all about VLSI. In this particular series of Verilog Project Development Series, we have developed the carry save adder and next we have developed the static RAM. And next in this particular session, we are going to see what do you mean by clock gating, and we are going to utilize this particular technique in one of the design. Now, basically, this clock gating is a power optimization technique used in digital design where the clock signal is basically selectively turned off for the portions of a circuit that are not currently used. So whenever you feel that clock is not necessary or not used, you're going to turn off your clock. Now, instead of basically continuously toggling the clock for every flip-flop in the chip, we are going to stop the clock to inactive blocks. And why clock gating is necessary? Because in digital circuits, the clock is going to toggle continuously, and for every clock transition, there is a charging or discharging of the capacitor that will definitely going to consume some dynamic power. So this we want to optimize it. So that's the reason we are going to use our clock gating. And clock network is one of the highest power consuming part of a chip. And in modern ASICs, clock network may consume 30% to 50% of total chip power. So reason clock toggles every cycle and reaches almost every flip flop and has a huge fan out. So if we stop this unnecessary clock toggling, it is going to save huge power, and this is the purpose of our clock hitting. Now, basically, what are we going to do in this particular clock gating is, let's say suppose if we have a finite state machine where we are going to detect a sequence 101, okay, using let's say Mealy FSM. Here in our code we are basically writing the FSM code for Mealy. I think, let me check it out. Yes, Mealy. Now for that, let's draw the state diagram. So if I apply reset, I'm going to an ideal state, and in the ideal state, if I'm going to give 0, I'm going to stay in the same state and my output will be equal to 0. And if I'm going to give 1, I'm going to next state, which is S1. And if my input is still 1, I'm going to stay in the same state and my output is equal to 0. But input is equal to 0, I'm going to next state S2. Now, in this particular state, if my input is equal to 1, then I'm going to S1 state since it's a overlapping sequence, and 0, I'm going to ideal state. So this is how my Mealy FSM is going to look like. This is what I'm going to implement. And if I'm going to implement this in Verilog, I'm going to have something known as present state logic, and I'm going to have something known as next state logic, and I'm going to have something known as output logic. So if you don't know about this particular coding style of FSM, I recommend you to please go through the Verilog development series, Verilog development series, which is already available on our channel. So this is basically a sequential logic which is going to decide your next state. So for every clock edge, you're going to decide what is your next state. I mean the present state. And this is next state logic, which is going to decide your next state. And it's a combinational logic, and we don't have an issue with this because it is not going to depend upon the clock. And coming to my output logic, it might be a synchronous logic. So it is again dependent upon your present state logic. Okay. Now, in the present state logic, we are going to include the mechanism which is known as clock gating. So in this particular present state logic, we are going to implement this clock gating technique for reducing the power. Now, how I'm going to introduce it? Let us see in the coding part. Now, this is my Mealy sequence 101 Mealy FSM sequence detection where I've declared my input as clock reset. This is my serial input. I have one more signal which is known as enable. So this enable will make sure to provide the clock to this particular module or not to provide the clock to the particular module. And detect is a signal which is going to tell me whether the sequence has been given or not. And there is one more clock which is known as G clock. This is nothing but my gated clock. Now, this G clock will be equal to clock and with enable. If enable is equal to 1, then only clock is given to the G clock. And if this enable is equal to 0, this G clock will be equal to 0. And this enable will be given from the test bench. And I've declared the parameters S0, S1, S2. These are the three states and state and next underscore state. So this is my present state logic. And if you carefully observe, I'm not using clock, I'm using G clock over here, or passage of reset, which is an asynchronous reset. If reset has been applied, then I'm going to S0 state, which is the first state, or else my state will be equal to next state. So depending upon the G clock only, I'm basically deciding my present state value. Now, coming to my next state logic, and output logic is also written in my next state logic only, which is a combinational logic. That's the reason I'm writing it down as star over here. Now, if I'm in S naught and depending upon my input, I'm going to S1 or else I'm going to S naught. And in S1 state, depending upon my input, I'm going to S1 or else I'm going to S2 state. How I'm writing this particular logic? By seeing this particular FSM state diagram. Depending upon this FSM state diagram, if you are in S1 state and if your input is equal to 0, you are going to S2 state, or else if your input is equal to 1, you are going to stay in the same state. And after this, what are we going to do? In the S2 state, that is what we have written, and default we are going to 0. That's it. This is my FSM, and the only thing which I've added over here is this G clock logic. That's it. And over here I've written the G clock. Now let's see in my test bench what I'm going to do. So in my test bench, I've written the inputs as rich and output as wire, and I've instantiated my design, which is my design, and over here I'm generating my clock, which is present, and I've applied my reset values, and enable is equal to 1. After desetting the reset, I'm making my enable is equal to 1. Now, so at first passage of clock, I'm going to provide D in is equal to 1. Next, I'm going to provide 0. Next, I'm going to provide 1. Next, what I'm going to do, I'm going to disable my clock using enable is equal to 0. Next, I'm again trying to provide the inputs whether it is taking it or not. And if you carefully observe, enable is equal, Din is equal to 1. And since you're disabling the clock, you're not going to change your states. That's it. Okay. So next, I've disabled the clock and I'm providing the inputs and all. Okay. So basically, this particular project will able to tell you that if the this is basically the demonstration of how you're going to use a clock gating technique, where this clock gating technique is used to help you to optimize the power by not utilizing the clock for every time, because sequence has been detected, 101 has been detected, and if you're not providing any input, design will run. Design will go on implementing the clock, and it is going to run forever. If even though if you're not going to provide the input, it is continuously checking for the input for the clock, because you have written over here always at the rate passage of clock. Normally, you're going to write down always at the rate passage of clock, right? So this always block will going on triggered, and it is going to check for this reset condition, or else if it is one or not, like that it is going on checking. Okay, so that's the reason here we are going to use a clock for optimizing the power. So let's run the simulation over here, and let us check what is that we are going to get. Over here we have applied our input 1 0 1, and enable was 1, that's why detect was equal to 1. And next 1 0 1, enable was 1, detect was equal to 1. Now again 1 0 1, but your detect output is equal to 0 because enable was equal to 0. Okay. So this is how this is about a clock gating, and this is how we are going to implement the clock gating technique. So that's all for this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.